Hello again, Math 20-1s. In today's lesson, we are going to define, examine, and look at various examples of geometric sequences. And you can find this lesson on page 43 in your Math 20-1 workbooklet. So to start off with the definition of a geometric sequence, it is a sequence where each term is obtained by multiplying the preceding term by a constant. So for example, if we look at this sequence where we have 3, which would be T1, 6, which would be T2, 12, which would be T3, and then 24, which would be T4. To get from one term to the next in the sequence, hopefully this is pretty obvious, but what you want to do is you want to multiply each one of these terms by 2. So notice this is different in comparison to an arithmetic sequence. An arithmetic sequence would be one where you need to add a common difference to get to the next term. An geometric sequence is going to be one where you need to multiply by a constant. And we do have a word for the name of this constant that we're going to multiply by. It's referred to as the common ratio. And we're going to use the variable r to represent it. If I want to calculate the value of the common ratio, a lot of times you can just look at this sequence and you can simply identify what it is you're multiplying by to get it. But if you're not totally clear on how to calculate the common ratio, the way to do this is you can take, for example, the second term in the sequence, and you can divide by the first term in the sequence. This is similar to how we figured out the common difference for an arithmetic sequence. For an arithmetic sequence, I could figure out the common difference by taking term 2 and then subtracting the previous term, which is term 1. And if you want to double check it, you could take term 3 and subtract the previous term in the arithmetic sequence. So for a geometric sequence, if I want to calculate the common ratio, you take the second term, divide by the first term. You could take the third term, you could divide by the second term, which is the preceding term. So that's r. Or you could take the fourth term, you could divide by the preceding term, which would be 3. So I could quickly confirm this if I wanted to. In this sequence, T2 would be 6, T1 would be 3. So 6 divided by 3 would give me a common ratio of 2. Or if you want T4 divided by T3, T4 is 24, and T3 is 12. 24 divided by 12 is also equal to 2. So you have a common ratio, that would be 2. We can, we can write that down. The constant value, which is the common ratio, is a 2. If we go back to this arithmetic sequence in terms of the common difference, if you want to write this down as like a general formula, you could write down D is equal to T of N. And then what you're always doing to figure out the common difference is you're subtracting the preceding term. So if the term you're starting with is T of N, then the preceding term would be T of N minus 1. If we look at the common ratio, we would take a term that we're interested in, which is T of N, and then we divide that by T of N minus 1, which is the value of the term that's right before it. It does say here that N needs to be greater than or equal to 2, and N is a natural number, which just means that the lowest number of terms you could possibly start off with in a sequence to calculate the common ratio is you'd need to know the value of T2 and you need to know T1. You couldn't, for example, go T1 divided by T0 because there is no such thing as the 0th term in the sequence. It doesn't make any physical sense. We're going to skip over example 1 and jump right into example 2. So it says, for example 2, for the following sequences, identify the type of sequence. Is it arithmetic or is it geometric? Depending on the sequence, identify the common difference or the common ratio. So your common difference is D. Your common ratio is R. And then I want to calculate the 5th term and the 6th term in each of these sequences. Okay, for part A, let's see if we can figure out what type of sequence it is without doing any calculations to start off with, and then we'll confirm it. So if I want to go from 8 to 24, there's a couple ways I could do that. I could multiply by 3. That would bring me to 24, or I could add 16. Now, if I want to go from 24 to 72, I need to do the same thing that I did in going from term 1 to term 2. So if you multiply by 3, well, yes, that actually would bring you to 72. If you added 16 here, that would not work. Okay, 24 plus 16 would be 40, which indicates that it's not as simple as just looking at a common difference to get to the next term in the sequence. So what this means is that it is indeed geometric. Now, if I want to confirm that quickly, we could calculate the common ratio. So the common ratio I can calculate by taking T2 and dividing by T1, which would be equal to 24 divided by 8. And then 24 divided by 8 would be 3. And if I want to double check that it is indeed common, the ratio, I could then take T3 and divide by T2. So T3 is 72, divide by T2, which is 24. 72 divided by 24 would also be equal to 3. So to get the values of T5 and T6, we just have to keep multiplying by 5 here. So T5 would be 216 multiplied by 3, which would be 648. And then T6 would be, you take this term and multiply by the common ratio, which is another 3, and that would be 1,944. And because we do have a common ratio, where r is equal to 3, this is what we refer to as a geometric sequence. We're multiplying by a constant to get from one term to the next. How about B here? Okay, to go from 108 to 72, if we're going to multiply by a number, we'd have to multiply by a fraction to get from 108 to 72 because we're diminishing this original value. So instead of worrying about that, let's see what happens if we consider this as an arithmetic sequence. So as an arithmetic sequence, to go from 108 to 72, you need to add negative 36. If we added another negative 36, would that form the third term in the sequence? Yeah, it would. 72 plus negative 36 would be positive 36. And if you added the common difference again, 36 plus negative 36 would be 0. If you did want to quickly confirm that, so D, the common difference, you could find by going T2 minus T1. So T2 would be 72. T1 would be 108. That would be equal to negative 36. And to double check that, I could calculate the common difference by taking term 3 and subtracting term 2. And that would be 36 minus 72 would also be negative 36. And because you have a common difference here, so common difference means a number that you keep adding to each term to get to the next one in the sequence. This is an arithmetic sequence. And we're adding a negative number to get to the next term in the sequence. So if I continue to add negative 36, then term 5 would be 0 plus negative 36, which would be negative 36. And then term 6 would be negative 36 plus the common difference, negative 36, which would be negative 72. C? Okay, we've got some fractions here, so this might make this a little bit more complicated. So let's consider this as like arithmetic first. So arithmetic would mean to get from negative 3 to 2, I'd need to add a number. So to get from negative 3 to 2, you'd have to add positive 5, or just add 5. Now, would that work in obtaining T3? There's not a chance, okay? So negative 3 plus 5 would be 2. 2 plus 5 would be 7. That's not this fraction negative 4 over 3. So it's probably going to be a geometric sequence, but we do need to confirm this. And it's not as obvious in this situation what the common ratio is going to be, so we're going to calculate it. Okay, so the common ratio, you can figure out by taking term 2 and dividing by term 1. So term 2 is 2, divided by term 1 is negative 3. So you'd have 2 over 3. I don't like to have the negative at the bottom, so I'm going to move it up to the top here. So R would be negative 2 over 3. We're going to double check this by taking term 3, which is negative 4 over 3, and then dividing that by term 2, which is 2. But this looks really ugly because you have multiple fraction signs within this expression on the right-hand side here. What I'd recommend doing when you have like these fractions is negative 4 over 3 represents term 3. The 2 represents term 2. So I'm actually going to rewrite it instead of as the division as a fraction. I'm going to write it with the actual division symbol. So we have T3 divided by T2. And then this would give you negative 4 over 3 divided by 2. And what I'm going to do here is when I divide by the second number, I'm going to multiply by its reciprocal. So if you take 2 and write it as a fraction, it'd be 2 over 1. Therefore, you'd have negative 4 over 3 multiply by, if I invert this, okay, you'd have 1 over 2. And then this would be negative 4 over 6. And if you divide both the top and the bottom by 2, it would also give you negative 2 over 3. So you have a common ratio that's negative 2 over 3. And because you have a common ratio that's negative 2 over 3, this tells you that the sequence is geometric. Now, to get term 5 and term 6 in the sequence, okay, so term 5, you would take term 4, which is 8 over 9, and then multiply by the common ratio, which is negative 2 over 3. And then that would give you negative 8 times negative 2 would be negative 16. And then 9 times 3 would give you positive 27. To figure out term 6, you then take term 5, which is negative 16 over 27, which, by the way, is a fraction that doesn't reduce. And then I'd multiply by the common ratio, which is negative 2 over 3. And this would give you negative 16 times negative 2 would give you negative times a negative is a positive. So that'd be 32. And then 27 times 3 would be 81. So term 6 would be 32 divided by 81. And I also don't believe this fraction reduces. So it'd simply just be left like this. So long story short, if it's arithmetic, you get to the next term in the sequence by adding a constant. If it's geometric, you get to the next term in the sequence by multiplying by some kind of constant number. And that constant number may be a fraction. I'm going to skip this investigation. What this investigation is what does is it tries to get you to derive a formula for the general term in a geometric sequence. Now, you'll recall for an arithmetic sequence, we've used this equation quite a bit. For an arithmetic sequence, an equation for the general term, the nth term in the sequence, was T of n is equal to A, which is the first term in the sequence, plus n minus 1 times D. We want a similar equation for a geometric sequence. And just because the lesson is long, I'm going to skip this investigation and simply just go down and show you what the equation is. So the formula for the general term of a geometric sequence, and this is the one we're mainly going to use right here, T of n is equal to A r to the power of n minus 1. So T of n is the nth term in the sequence that I'm interested in. A, you can either write it as A, which is the first term. You can write it as A or T1. I generally like to write it as A as opposed to T1. R represents the common ratio, and then n represents the term in the sequence that you're actually interested in, the term that you want to consider. Okay, so we're going to play around with this equation a little bit right here. And like I said, if you want, you can go through the investigation to derive it, but I don't really feel like it's necessary. Third example, determine the formula for the general term and then calculate the indicated term for each of the following. All right, so if you look at this term here, or so the sequence here, to get the general term formula, I need to know what the value of A is, which is the first term in the sequence. So here, that A value would be 5. And I also need to know what the common ratio is. Now, the common ratio in this one is really obvious. How do you go from 5 to 15? You multiply by 3. Let's double check it. If you multiply by 3 again, do you get 45? Yes, 15 times 45 would be 3. So your common ratio here is R is equal to 3. We want to calculate Tn. So we're going to calculate, so I'll say when n is equal to 9, we want T9, the ninth term of the sequence. We'll start off by writing down the general term formula. So for the geometric sequence, T of n is equal to A, R to the n minus 1. And we're going to start to plug numbers into the equation now. So we want the ninth term in the sequence. So I'm going to write down T9. And that would be equal to A, which has a value of 5. I'm going to sub it in brackets. R, which has a value of 3, to the power of n. We're figuring out the ninth term in the sequence, which is 9 minus 1. Now, to calculate this, I need to follow the correct order of operations. So I need to deal with the exponent first. So I'll do the subtraction on the exponent, which is going to turn this into 5, and then 3 to the power of 8. And then I need to do 3 to the power of 8 before multiplying by 5. Now, you could just plug that into your calculator and just determine it immediately. If you'd rather break it into an additional step, you can write it down as 5 multiplied by 3 to the power of 8. And 3 to the power of 8 is, let's see here, I think it's 6,561. I just want to double check that. Yeah. And if you multiply that by 5, it would then give you the value of the ninth term in the sequence, the geometric sequence. And then that would be 32,805. This next one, again, a little bit tougher because you got fractions. But again, fractions aren't that bad as long as you kind of just slow down and kind of just break it apart and use the reciprocal trick to figure out what the common ratio is. So some people may be able to look at this and identify immediately what you're multiplying by to get to the next term. Now, if you're not sure how to do this, you can always just go to determining the common ratio by taking a term, for example, T2, which would be -1/6, and divide by the preceding term, which is 1/3. Okay, so I've got that ugly multiple fraction thing. So I'm going to replace this fraction sign, the one that separates the -1/6 and 1/3, with a regular division symbol. So that's -1/6 divided by 1/3. And then we're going to multiply by the reciprocal of that second fraction. So I'm just going to invert it. So it's 3/1. And that would be -1 times 3 is -3. 6 times 1 would be 6. And to reduce the fraction, you would just divide both the bottom and the top by +3, and that would give you -1/2. To double check this, you can take the third term in the sequence, which is 1/12, divide that by the second term in the sequence, which is 1/6. Again, you're taking a term and dividing by the preceding one. So this would be 1/12, and then divide by -1/6, which would be equal to 1/12, and I'm going to invert that one. I'm going to multiply by the reciprocal, which would be multiplied by 6/-1. So that would be 1 times 6 is 6, divided by 12 times 1 is -12. If you move the negative up to the top and you reduce the fraction, dividing both the top and the bottom by +6 would also give you -1/2. Okay, so the value of R is -1/2. And the value of A is the first term in the sequence, which is 1/3. Now, we want to calculate T7. So I'm going to replace n with 7, and that's going to allow me to calculate the seventh term. Let's write down the general formula for a geometric sequence. That's T of n would be equal to A, r to the n minus 1. And now we'll start making substitutions. So this would be t of 7 would then be equal to a, and I'll sub it in brackets, which is 1/3, multiplied by r, which is -1/2, and then to the power of n, which is 7 minus 1. So this would then give me t7 is equal to 1/3. And then, again, deal with that exponent first. So 1/3 multiplied by -1/2, the common ratio to the power of 7 minus 1, which would be 6. Again, you can plug this into your calculator in one shot if you'd like to do it like that. Just make sure you have the brackets surrounding the fraction and the negative sign. If you prefer to break it down one step further, you could write down 1/3. And then -1, to apply this exponent to the fraction, it has to go to both the numerator and the denominator. So -1 to the power of 6 would just be 1. And then 2 to the power of 6 would be 64. So therefore, if you want to calculate T7 would be 1 times 1, which is 1. And then 3 times 64, which would be 192. Okay, and that's the 7th term in the geometric sequence. Okay, so far it shouldn't be too bad. Yeah, the fractions can be a little more complicated to deal with, but otherwise utilizing the general term formula isn't really all that much different than using the general term formula for the arithmetic sequence, except now you have n as an exponent as opposed to like n as not being an exponent. Now we'll look at a bunch of different types of examples. Aside from just like flat out calculating like the nth term in the sequence. So this example gives you a bunch of terms in the sequence, including the last term in the sequence, and it wants us to kind of go backwards in a way to figure out how many terms are in the geometric sequence. So we can go ahead and label this. So 32 would be A, 64 would be T2, 128 would be T3, and then 16,384 would be Tn. I have to write it as Tn because I don't know how many terms there are in the sequence. That's what we're going to try to figure out. Okay, now it says use the general term formula to write and simplify an equation which could be used to determine the number of terms. And again, the number of terms is going to be represented by little n. To use a general term formula, though, I need to know what the common ratio is. So this one right here, it's not too hard to see what the common ratio is. How do you go from 32 to 64? You multiply by 2. How do you go from 64 to 128? You multiply by 2. So the common ratio is going to be R is equal to 2. And if you're not sure about that, you can always calculate it by going T2 over T1. So that'd be 64 over 32, which is 2, or T3 over T2, which would be 128 over 64, which is also 2. Okay, A is 32. Let's write down my equation. So I'd have Tn for a geometric sequence is A, r to the power of n minus 1. And I'm going to substitute everything I can into this equation, including the value of Tn. And I know the value of the last term in the sequence is 16,384. So if I plug that in, it would then be 16,384 would be equal to A, which is 32, and then multiply it by 2 to the power of n minus 1. Now, I could leave the equation like this, but I want to try to get n as close to being by itself as possible. So one thing I can do right here is I can actually get rid of this a term. So this 32, I can divide both sides of the equation by 32. So I'm going to divide by 32, and I'm going to divide this by 32. And if you do this, it would then give you 512 is equal to 2 to the power of n minus 1. Now, I'm just going to box this equation right now, and then we're going to solve for n using a couple of different methods. Now, unfortunately, we don't, at this point, possess the ability to solve this algebraically, because to solve it algebraically, you need to utilize something you'll learn in Math 30-1, which is referred to as logarithms. So the methods we're going to use to solve n at this level is we'll use our graphing calculator in part C, but there is a way that they refer to as guess and check here. I don't know if I'd call it guess and check as much as it's kind of like a semi-algebraic method of doing this. But here's how we're going to do. I'll illustrate here illustrate here how we can actually solve for n without using a logarithm, which again you'll cover in Math 30-1. Okay, here's a general idea. Let's write down this equation. 512 is 2 to the power of n minus 1. Now, what I want to do is the number on the left-hand side of the equation, I want to rewrite it. I want to rewrite it as a base of 2. Why a base of 2? Because on the right-hand side of the equation, you have a base of 2 raised to an exponent of n minus 1. So whatever the base is that's attached to the exponent, we want to see if you can write this number on the left-hand side of the equation with a common base. So the question right here is, well, can you actually write down 2 to the power of something is equal to 512? And I suppose this is where guess and check kind of comes into play. Again, I don't know if I'd call it this method, but let's just plug in some numbers and see if we can get 2 to the power of something is 512. Okay, so I'll go to my calculator here. Let's try like 2 to the power of 5. Okay, that's 32, so no. 2 to the power of 6 is 64, no. 2 to the power of 7 is 128, no. 2 to the power of 8 is 256. Okay, we're getting close now. 2 to the power of 9, yes, it is 512. So I can actually write down 2 to the power of 9 is 512. If I take this equation now and rewrite it, 512 I can write down as 2 to the power of 9, and that would be equal to 2 to the n minus 1. You might be wondering why exactly I did this. Well, here's the reasoning. If both sides of the equation have a common base, which they now do, they both have a common base of 2, you can actually solve the equation just by taking the exponents and setting them equal to each other. So with the common bases of 2, I can set the exponents equal to each other, which would give me an equation that is 9 is equal to n minus 1. And then to solve for n, which is the number of terms in the sequence, just add 1 to both sides of the equation, and that would give you n is equal to 10. Now, this method works fine as long as you're actually capable of writing the number on the left-hand side as a common base, but you're not always going to be able to do that, okay? If you can, it's great. If not, algebraically, you're going to have to use logarithms, which, like I said, you'll learn in a future math course. We also can use our graphing calculator to do this, and the graphing calculator does not require that number on the left-hand side to be written as a common base. So let's write this equation out again, and we'll set the graphing calculator up. So you've got 512 is equal to 2 to the power of n minus 1. In my graphing calculator, I'm going to input 512 into y1. So the left-hand side of the equation is going to go into y1. And I'm going to input the right-hand side of the equation into y2. So that's going to be 2 to the x minus 1. We have to use the variable x instead of n because that's kind of like the default variable that the calculator has. And then after we plot these, we're going to use the intersect feature to determine the value of x, which will give you the value of n, the number of terms in the sequence. Okay, so let's go over to the graphing calculator now and do this. So go into y1. If there's anything in y1, y2, etc., just clear it all. So in the place of y1, I'm gonna write down 512. In the place of y2, I'm gonna write down 2, and then to the power of Okay, make sure all of this is in the exponent of the 2. So you have x minus 1. And I'll just go to the standard zoom and see what happens here. Zoom standard, zoom 6. Now, this isn't good enough to actually calculate the intersect, because for the calculator to calculate the intersect, you have to actually be able to see the intersection point between two different functions here. So right now it's not good enough. I'm going to have to adjust the window setting. So the immediate question is, well, what do I adjust the window setting to? Well, let's look back at our equation for a second. One of the equations is y1 is equal to 512. Now, if you think about what that equation actually is, okay, that would just be an equation that is y is equal to 512. That would just be a horizontal line that passes through the y-axis at 512. So I at least need to be able to see 512 on the y-axis. So I'm going to go to my calculator and I'm going to adjust the y maximum. So go to the window and I'll change the y maximum to a number where I'm guaranteed to at least see 512 on the calculator. So I'll change y maximum to 600. Okay, now I'll go ahead and graph that. And I pretty much can see the intersection point. It looks like it's on the far right-hand side of the calculator screen. But I want to definitively be able to see the intersection between this red and this blue line, this red curve. So I'm going to change the X max just for make it a little bit bigger so I can actually see that. So I'll go to window and I'll change X max to any number bigger than 10. I'll just double it. I'll make it 20. And then go ahead and graph it. And now I can for sure see the intersection point. So now we're ready to actually use the calculator intersection feature to determine this intersection point. So to do that, I hit second and then trace, which is calculate. And then on my calculator, I'm going to go down to number 5, which is intersect. Okay, now I see the cursor on the blue line. I'm going to get it as close to the intersection point as I can. So bring it over to the right here. Okay, hit enter. And then same thing, I want to bring the cursor on the curve as close to the intersection point as possible. Get it to guess the answer, and it tells me that x is 10, y is 512, which is what I expected anyways, because we already determined this in part B. So let's write down when x is 512, y, oh, sorry, other way around. When x is 10, y is 512. And the value of x is the value of n, because we replaced x with n when we plugged it into the calculator. So n, the number of terms in the geometric sequence, would just be equal to 10. Okay, we got a few more examples. So I'm going to clear this. I don't know why this is actually on here. Sorry about that. Now, we did this before with arithmetic sequences where we inserted arithmetic means between a couple of different numbers. So I'm going to do the same thing with for a geometric sequence. So the way to do this is to insert 4 geometric means between these numbers. I'm going to write the 2 numbers out. So I'm going to write down 81. And what I want to do is I want to put in 4 numbers. So 1, 2, 3, 4. 4 numbers between this term, which has a value of 81, and this last term, which has a value of 1 over 729. So the 4 geometric means are going to be 4 numbers you put between these 2 values that are given, that when you multiply the first term by the common ratio, then by the first arithmetic mean, the second one, the third one, the fourth one, you eventually end up at that last number, which is 1 over 729. So the way to write down these missing terms, so we have we have T2, which would be the first arithmetic mean. T3 would be the second arithmetic mean. T4 would be the third arithmetic mean. T5 would be the fourth arithmetic mean. And then T6 is going to be the last term in the sequence. To figure out what these missing terms are, I need to know what the common ratio is. Okay, so we got to calculate that. Now, we do have enough information to do this. So I know that A is 81. I know that when N is equal to 6, the value of term 6, T6, would be equal to 1 over 729. So I'm going to write down the general term formula for a geometric sequence. That's Tn is equal to A r to the n minus 1. And I'm going to plug all this information into this equation and see if I can calculate the common ratio. So this would then be, well, we're finding we're going to replace n with 6. So we're going to have T6 would be equal to A r to the 6 minus 1. So this would then be, we can actually write down, we can replace the A immediately too. So let's do that. Actually, we'll do it on the next step here. Okay, this would then be T6, which has a value of 81. A, which has a value, T6 isn't 81. Whoops. T6 is 1 over 729. Would be equal to A, which is 81, multiplied by R to the power of 5. We want to solve for the common ratio. Okay, so to get the common ratio, R, I need to get rid of this 81. So I'm gonna get rid of that 81, just dividing both sides of the equation by 81. So we'll go divide by 81, divide by 81. 1 over 729 divided by 81, you can determine that by, again, multiplying by the reciprocal of 81. If you prefer just to plug into your calculator, you can also do that. So you could write down the original number on the left-hand side, which is 1 over, actually, this is not going to work here, 1 over 729, and then divide it by 81. I think it's going to give you too small of a decimal number for the calculator to actually convert it into a fraction. Yeah, it doesn't do it for you. Okay, so we'll actually have to do this by hand. No problem. Okay, so what this would look like is, let's just deal with this left-hand side. So this would be 1 over 729 divided by 81. So that'd be 1 over 729 times, we write the reciprocal of 81. We can write down 81 as a fraction, 81 over 1. So that'd be 1 over 81. And then this would be 1 over, it's going to be a large number. So we have 729 times 81. So it'll be 1 over 59,049. Okay, so let's rewrite my equation out here now. So on the left-hand side, I would have 1 over 5,949 would be equal to r to the power of 5. To calculate the common ratio, I don't want to know what r to the power of 5 is. I just want r. So I need to get rid of that exponent 5. So the question here is, what exponent are you going to raise r to the power of 5 of to get rid of that 5? Well, the answer to that is 1/5. Because if you go 5 times 1/5, it would be 5 over 5, which would just be an exponent value of 1. Whatever you do to one side, though, you also have to do to the other sides. We're going to raise this to the power of 1/5, and we're definitely going to need our calculator to do that for us. So let's go to the calculator, and we have 1 over 59049, and we're going to raise it to the power of, again, just make sure that all the fractions in the exponent, and that gives me 0.111 repeating. I want to see if I can convert that into a fraction. So I'll hit the math button and then FRAC. And this turns it into a fraction of 1/9. So my common ratio the 5 up here, the 5 down there cancel. So you'd have r to the power of 1, or r would just be equal to 1 over 9. Now, Because we know what the common ratio is, to get the arithmetic means, or these missing terms right here, we just start with the first term and just begin multiplying by the common ratio. So I'll go back to the graphing calculator. Because I'm going to multiply by the common ratio a bunch of times, I'm actually going to store the common ratio as a variable in the calculator. So I'm going to write down 1 over 9. And I'm going to hit this STO button. And then I'm going to pick X. And what this is going to do is it's going to take the common ratio, 1 over 9, and it's going to store it as a value of X. So anytime now when I hit X, it's going to bring up 0.111. Okay, so if we go back to my sequence now, the first term in the sequence is 81. To figure out the second term in the sequence, multiply by the common ratio. So 81 times the common ratio would just be 9. Okay, so T2, which is the first arithmetic mean, the first geometric mean, would have a value of 9. To figure out the second geometric mean, multiply by the common ratio again. So we'll take that answer and multiply by X again. Okay, that's equal to 1. So my second geometric mean has a value of 1. To figure out the third geometric mean, multiply by the common ratio, which I've stored as X again. Now this gives me a decimal number, which we already know that 0.1 repeating is 1/9. So we can go back here and just write down this is 1 over 9. And then we're going to take that and multiply it by the common ratio again to get the fourth geometric mean. Okay, that's an ugly decimal number. Let's see if the calculator will actually convert this to a fraction. It does. It's 1 over 81. And then we'll multiply by the common ratio one more time, because if we've done this correctly, then we should get this last term here. So if I multiply by X, get an ugly decimal number, convert to a fraction, and it should be 1 over 729, and it is. Okay, so I have inputted my 4 geometric means. So it's 4 numbers between these two values, where if you take the first number and start multiplying by the common ratio, you're eventually going to get that last term that you have in the sequence. Okay, a few more of them. For a few more of these, we have problems now where we don't know what the first term is and we don't know what the common ratio are. So let's see what we have. Example 6 says 3 consecutive terms in a geometric sequence are X plus 3. So that's A. X, which would be T2, then X minus 5, which is T3. Use the concept of common ratio to figure out, first of all, what the value of X is, and then determine the 3 terms. All right. So here's what we know. We know we can calculate the common ratio by taking term 2 and dividing by term 1. Again, A is the same thing as term 1. You can also calculate the common ratio if you take term 3 and divide by term 2. Common ratio is always a term divided by the preceding term. So T2 over T1 or T3 over T2. I'm going to focus on this portion of the equation, T3 or T2 over T1 and T3 over T2. And I'm going to replace T2, T1, T3 with these different expressions here, the X plus 3, the X, and the X minus 5. So T2 is X divided by T1, which is X plus 3. T3 is X minus 5. Divide that by T2, which has a value of X. And now I have to solve this equation for X. The easiest way to do this is to cross multiply. I want to get the stuff out of the denominator. So I'll bring this X up to the top here. These two binomials, I'll put them in brackets. And then I'll move this X plus 3 up to the top on that side. So what this will do now is it'll become X times X is X squared. And this will be equal to, you're going to have X plus 3. And you're going to have X minus 5. Right-hand side of the equation, we need to expand it by foiling it, binomial expansion. So this would turn into X squared is equal to, first times first is X squared, Outside times outside would be x times negative 5, which is negative 5x. Inside would be positive 3 times x, which is plus 3x. And then last times last would be positive 3 times negative 5, which is negative 15. Okay, if I simplify the right-hand side, this would give me x squared is equal to x squared. Negative 5x plus 3x be negative 2x. And then minus 15. Now, it seems like I'm going to have to solve a quadratic here, but you actually don't need to, because if you subtract x squared from both sides of the equation, so minus x squared, they would just cancel off. So it's not something that needs to be, you need to concern yourself with. It would then be 0 is equal to negative 2x minus 15, which is a linear equation. And we solve a linear equation by getting the constant term by itself and the variable on the opposite side. So I'll get the constant term by itself by adding 15 to both sides of the equation, which would give me 15 is then equal to negative 2x. And then to get x by itself, I'm going to divide both sides of the equation by negative 2, divide by negative 2, and then I would have x would be equal to, I'll move that negative sign up to the very top here. So you're going to have negative 15 over 2. That's part of the solution I want, negative 15 over 2. Now, I also need to figure out the value of these three terms, because the three terms are written in terms of the unknown value of x, which I just determined. Okay, so a has a value of an expression, x plus 3. I'm going to replace x with negative 15 over 2. And I'm going to add 3. Because this fraction has a denominator of 2, I'm going to write 3 with a denominator of 2. So 3 with the denominator of 2 would be adding 6 over 2. And then that would give me a would be equal to negative 15 plus 6 would be negative 9. Negative 9 over 2. So that's the actual numerical value of the first term in the geometric sequence. The second term is easy because the second term, t2, if you look up here, it is just x. So t2 is equal to x, which is negative 15 over 2. We'll go ahead and we'll box that. And then t3 is x minus 5. Replace the x with negative 15 over 2. And I want to rewrite negative 5 with the denominator of 2 because I want to be able to combine these two fractions. So negative 5 with the denominator of 2 would be negative 10 over 2. And then that would be t3 is negative 15 minus 10 is negative 25 over 2. So t3, negative 25 over 2. So those are my first three terms in this geometric sequence. All right, one more. Okay, it tells me the fourth and the seventh terms in a geometric sequence are negative 54 and 1458. Well, let's write that out. So write down T4 is equal to negative 54. And we'll write down T8 is equal to 1,458. Use a system of equations to determine the value of the first term. So that's A, and the common ratio, R. And then also it wants the formula for the general term of the sequence. Okay, so let's start off by writing down that general term. So that general term is T of n for a geometric sequence is A, R to the power of n minus 1. Now, I'm first of all I'm going to go through this equation here by replacing n with 4, n with 4. What that'll do is it's going to turn this into T4 would then be equal to A R to the 4 minus 1. I know what the value of T4 is. It's negative 54. So I then have negative 54 would be A R to the power of 3. I'm going to box this equation right now. I'm going to call it equation number 1. I can't solve it because you have two variables in one equation. So A is an unknown variable, R is an unknown variable, two variables, one equation. There's actually an infinite number of solutions. I'm then going to go through the general term formula, but this time I'm going to replace n with 8. Okay, n is going to be replaced with 8 this time around. So this would then look like T8 is going to be equal to A r to the power of, oh, sorry, it's not 8, it's 7, the seventh term in the sequence. Let's fix that right away. There we go. T7. Let's fix this here. Okay, T7. Okay, AR to the 7 minus 1. We know the value of T7. It's 1458. And this would be AR to the power of 6. Once again, if you view that equation on its own, you can't solve it because you have two variables in one equation. So I'm just going to box this one, and I'm going to call it equation number 2. There are various ways to solve this. The method I'm going to use is elimination. The thing is, in this situation, the easiest variable to eliminate is going to be A. So the question is, well, what should you do these two equations to properly eliminate it? In this situation, you actually want to divide. You want to divide the two equations together because then you're going to go A divided by A, and that's going to cancel the A's off. Now, you could go equation 1 divided by equation 2, but that's going to give you an ugly fraction on the left-hand side because you're going to have negative 54 over 1458. I suspect if we go equation 2 divided by equation 1, it's going to be a little bit easier to deal with in terms of both the number on the left-hand side and also combining the exponents on the r's. So I'll write down here, eliminate A. And the way we're going to do that is we're going to take equation 2 and we're going to divide equation 1. So equation 2 is 1458 is equal to AR to the power of 6. We'll stack the equations. We'll write the equation 1 beneath it. So negative 54 is equal to AR to the power of 3. And what I want to do is I want to divide that second equation. I want to go equation 2 divided by equation 1. So we're going to divide this. Okay, let's see what we get. Let's deal with the left-hand side first. So I'm going to go 1458 divided by negative 54. So 1458 divided by negative 54. That's negative 27. So you have negative 27 would then be equal to A divided by A would just cancel. That'll give you 1. Now, r to the 6 divided by r to the 3, we need to use our exponent rules. If you're going to divide two terms that have a common base, you just take the exponents and you subtract them. So that would be r to the power of 6 minus 3. If we simplify this a little bit, it would then be negative 27 would be equal to r to the power of 3. Now, I don't want to calculate r cubed. I want just r. So I need to get rid of that exponent. So we're going to need to raise this term here to an exponent that gets rid of the 3. To get rid of that cube, you're going to raise it to the power of 1/3. And you do that to both sides of the equation. Again, the idea right here is if you raise it to the power of 1/3, the 3 on the top and the 3 on the bottom would cancel if you multiply those two numbers together. So this would then give you r is equal to negative 27 to the power of 1/3. Now, raising a number to the power of 1/3 is determining a cube root, and you definitely could have negative cube roots. The cube root of negative 27 is going to be r is equal to negative 3. Again, you can also plug that into your calculator to determine it. So put it in brackets, negative 27 raised to the power of 1/3 is equal to negative 3. Now, we also need to figure out what the value of A is. So once you get R, we've solved the system now pretty much. You can plug it back into equation 1 or equation 2 and then just solve the equation for A. I'll plug it into equation 1 because it looks a little bit easier to deal with. Although that's a way of double checking to make sure you solve the system correctly. If you plug R into both equation 1 and 2, you should get the same value for A here. So I'll say sub R equals -3 into equation 1. So that'd be -54 is equal to A, which we're going to calculate in a second, and then R, which is -3 to the power of 3. So this would be A times -3 cubed would be -27. And then to solve for A, just divide this by -27, divide this by -27, then you get a nice value for A, which is A would be equal to +2. Okay, now we're pretty much done. It says, give me the formula for the general term of the sequence. Okay, so the general term we're going to write down the general term formula, which is T of n is equal to A R to the n minus 1. And all we have to do is just plug in the values of A and R, and that gives me the general term formula. So this would then be T of n would be equal to A, which is 2, multiplied by R, which is -3, to the power of n minus 1. And this general term formula can be used to determine any term in the geometric sequence. You just need to plug in whatever n value you're interested in. So if you wanted like the 17th term in the sequence, you'd plug in T17, then up here, the n you'd replace with 17 as well. All right, that's the end of this lesson. And you can practice all these concepts, or I shouldn't say concepts. The concept is really just one thing, dealing with geometric sequences, by completing on page 47, do numbers 4a and b, do number 5, do number 7, do number 8, number 12, number 15, number 17. So you got 4a and b, 5, 7, 8, 12, 15, 17. And I'll talk to you in the next lesson.